Thanks very much. I know we're running a bit late, and I'd like to say that I will talk fast and catch us up, but those of you who know me know that I'll talk fast and do nothing to help us get back on time. I did want to talk about Frontera, which I talked about a little bit at last year's meeting when it was speculative, and now it's a real thing, so I want to talk about our experiences with it. The subtitle here, I can confirm that it's 2019 and no user still knows how to use a file system. And if you're one of my users in the audience, I should pretend to apologize, but I don't really. I should say Frontera is one of 5 DDN deployments that we have at TACC. And given that we have 5 of them, I would like for Paul and Alex for you to not make enough money to buy a Gulfstream on our account. But I do think the next time, yeah, Paul knows that's not going to happen. So, yeah, a winglet, yes. But I do suggest the next time Larry needs a quote, you guys suggest barter. You know, the exchange of goods might be the right way to do this. So, so Frontera now does exist. And if you've heard me talk about this recently, including twice more today, I promise that only the first 30% of the slides are the same, and the last 5%, and the middle part is all different. So just a quick update on TACC. For those of you who don't know us, Texas Advanced Computing Center at UT Austin. At this point, we're a couple hundred people, 12 megawatts of data center because of the problems that Larry was just talking about, probably on our way to 30 megawatts of data center. And we put out about 7 billion compute hours a year, but we do have about 5 billion files and 100 petabytes of data for many thousands of users on many thousands of projects, although Frontera is restricted to the very largest ones, and I'll show a few of those, including a hypersonic wing that we're working on as some of the sort of first few months of usage on that system. So just Frontera in a nutshell, conveniently it did not move on the top 500 list when it came out today, which I appreciate because I would have had to change a whole bunch of slides if it did, and obviously I think at this point the list has more to do with geopolitics than hardware, so just as well keep the slide. So, but yes, it's the number 5 ranked system in the world. Stampede, by the way, is number 18. Somehow it went up the list, even though it's 2 years old. I'm still working on why that happened. So, and then Longhorn is 120 on the list today. So we have, I think, 3 of the top 5 academic at this point. So, but it's brand new. We managed to get it onto the list in June, but we had just gotten the hardware and run LinPack. Now it's really ready for prime time, and it's been running real science the last few months that I'll tell you a little bit about. So Frontera is actually a set of machines. The 39 petaflops of compute is the Intel Xeon-based part, but we also have some GPU subsystems. The Longhorn subsystem there actually is its own slot on the top 500 list at 120 because it's power. And you don't give users the same home directory between x86 and power because they will inevitably run the wrong binary, right? So you have to treat it as a separate system and give them a separate file system to do it. But and then we have a whole host of file systems, which I'll spend a number of slides on, fast interconnect, all the things you would expect. So we really think of it as an ecosystem. One sort of recent thing is with all the different services that we have to run in front of the machine, we've really bumped up that front layer where we used to put like 4 login nodes on the system. We now have like a rack of hardware for running various kinds of service nodes and virtual login nodes in front of it. So get to the storage in just a moment. So promise to spend the bulk of the time there, but there's a few words, since, particularly since Larry finished up talking about trying to cool these things. We have gone to Cascade Lake, the 8280s from Intel. This is a 205-watt chip, so we have officially given up on air-cooled infrastructure at this point. So everything is liquid-cooled. That's a picture of the node. The cooling solutions come from CoolIT and CoolTera. In fact, you'll notice when I show the switches, even the switches are liquid-cooled at this point. So our core switches are pushing 30 kilowatts, but so we do run liquid directly across the sockets at this point because that's 410 watts of socket in that quarter U node, and then rear door to cool the DIMMs and the power supplies. But 28 cores, back up to 2.7 gigahertz. We've sort of decided that the higher the clock rate, the better. And to some extent, it's screw the power on that. But in reality, that we've discovered that peak flops per watt look a lot better in the lower frequency parts. And you can, there's that factor of 3 relationship in the power equation. It says every 10% frequency, you increase power 30%. But user codes run more efficiently on the high clock frequency chips. So the sort of science per flop or science per watt that you get out of the higher clock rate parts is worth the extra power because we get work done faster. So in the end, we use less watts with the higher intensity parts, but it does mean we have a whole lot of infrastructure around that. you think flying near Mach speed is hard. Try and cool 60,000 watts in something about the width of this podium. So we have 91 cabinets at 60 kilowatts a rack. So running LinPack is a 5.4 megawatt exercise. And that's just the compute racks, and that's actually measured, not a theoretical number. And that's exclusive of storage and the GPUs and everything else. So you'll see some of the GPU nodes. We're doing full immersion now. We've switched to liquid cooling. We're buying about a third of the power from wind, but we have Dr. Seuss's worst nightmare of piping out there in the back to actually cool this thing down. Yeah, Larry's nuke experience is going to come in handy in other parts of computing soon. So the interconnect is from Mellanox, and we did do the 200 gig thing. That is actually the current generation. 100 gig to the nodes, but 200 gig to the core. And 200 gig to the storage, all over HDR. We have a little bit of oversubscription in the compute racks, none to the storage racks. That is one of the core switches. Again, you'll note that it is also liquid cooled. You see the CDU, the chilling distribution unit hoses on the bottom there, and there's a hose into each line card to cool the electronics in those as well. The machine is actually pretty much room neutral with all of it's about 6 megawatts of infrastructure, and I could turn off the air conditioning in the room as long as I keep the underfloor chilled water going to the CDUs, and you'd never notice. So, except for the other racks across the hall. But anyway, so the nice thing about the 200 gig is we did do, we have a little more than 8,200 cards in the fabric. We have 182 top of rack switches, 6 core switches, 50 miles of cable. It's actually less than Stampede had by about 30 miles because we were able to raise the rack density and take out the in-row chillers, so we get less cable latency and lowered the latency. And because we're doing 200 gig switch to switch, it took a mere 3,276 fibers to put it together, which, believe it or not, is a good number. But that's all the boring part. Let's talk about the storage, right? That's what we're here to do. So the storage is all from DDN for all the different tiers, actually including all the way out to the archive at this point. It is all Lustre. It is all POSIX compliant. We do have a little burst buffer with IME on the flash part at the moment, but the long-term plan is to make that just a POSIX compliant Lustre file system as well. We have about 50 petabytes of disk. We have about 3 petabytes of flash. And obviously, when you design one of these, you expect your users to take advantage of striping and write big files, and everything's a happy 10 megs. No, none of that is actually true. So if you look at our actual file system usage, the happy note here is if you just take Stampede 2 Scratch, which has about 2 billion files on it at the moment, it's about 20 petabytes. Actually, the usable is about 15, but the numbers work out to our average file size is close to 50 megabytes, which would be a good one. And somebody left their phone up here? Probably a DDN person left their phone up here. So they'll figure it out. So 50 megabytes would be a nice file size, except that I know we have some 4 terabyte files on there, right? Several million times the average. So the median file size is not a happy 50 megabytes. In fact, it might look a lot more like 4K. It's a big data problem, so I haven't actually computed it. But there's an awful lot of several K files that we're trying to deal with on Lustre. And so I have come to believe over 25 years of doing this that, I'm not one of the users of the system, but if I were to guess what their average I/O code looks like, I think it looks a little something like this. So they do a while one, and they do a fork, and then they do an open. Optionally, they do a close, although I think most times they don't really bother with the close. They just leave the files open. Usually it's in a very tight loop. I hear there's some reading and writing, but it seems to be not important compared to the number of opens and closes that happen. And then you run like 80,000 copies of that, right, with MPI run. And that seems to be the normal situation that we see on the file systems that we have. So we've made some changes, right? And so it occurred to us, and there's the actual file systems there. So by the way, I consulted heavily with Paul on design of front panel lights, where I insist that DDN is leading the industry in front panel light design. The Dell racks are just boring. Nothing blinks. When we really want to show stuff off, we put the DDN racks in the front near the glass. So you always get preferred space in our data center because you guys are good at this. So, the boring stuff goes in the back. What we realized is that sort of the history of HPC is we have scaled our file system size to get our target bandwidth, right? So for many, many years, the only way we got 100 gigabytes a second or whatever bandwidth target we were after, often a lot lower way back when, was to run several thousand spindles concurrently, multiply the bandwidth, and you get the bandwidth you want. Capacity was almost free at that point, right? Really, we were buying bandwidth, right? So And mostly in our environment, that's to support concurrent usage of the file system, right? You have the occasional user who's pushing one dimension. You know, my WOW1 fork case is at the IOPS case, but our pathological I/O case, also known as the typical one. You know, some users are pushing bandwidth, some are pushing capacity, but you're never using all the capacity really for one user, except the IOPS and the bandwidth, right? But capacity is for many, many users who are resident on the file system at the same time. But now, in the age of Flash, why are we building one big file system, right? We can scale our bandwidth and our capacity as independent variables, right, with the things we buy. So there are a lot of devices dinging up here. There's an iPad, there's a phone. None of this is mine. Somebody's laptop. They're different people because the messages are coming in at different times. So so if you're in trouble with somebody, then, and a microphone, there's all sorts of electronics. It's really fine. I'm just, you know, it's something to, I have a very short attention span, so the more things that beep, the worse off we are in terms of the talk. So, but yes, but nonetheless, since we can buy bandwidth from Flash and we can buy capacity with disk, and no one user is using all the capacity and all the bandwidth and all the IOPS at the same time, we've stopped building one big file system. It just doesn't make sense. So what we did is just partitioned it, right? So we still buy the capacity that we need, which we figured was about 50 petabytes. We had a target of hitting over a terabyte a second. We're actually at around 1.2 terabytes a second to the Flash, but our initial design target was about a terabyte. And we shot for a little higher, but we only have a few users that hit that sort of terabyte a second requirement or the high IOPS requirement. So instead of having one scratch, we have 4, 3 disk pools of scratch, and then the Flash scratch, the super fast scratch. And the disk pools, we have about 100 gigabytes a second, which deals with your run-of-the-mill HPC user, which I'll talk about. And then we have the 1.2 terabytes per second to Flash. So if you have this sort of I/O case, and we all know that our long-term weak point has been file systems, mostly because it's the one thing that we force users to share, right? You can isolate compute nodes. We can isolate memory bandwidth. A user can trash their node, but they can't trash other people's nodes because they're somewhere else, right? And they don't have access to them. But the file system is the truly shared resource and the one thing that a user can hit that affects other users. So now at most you can trash, like we also have 3 home file systems. So you can trash 1/7 of the file systems and not all of them when you run your WOW1 fork open code. Actually, we've wrapped open with a library now so that you can't do more than 5 opens per second, or 5 opens per 100 milliseconds, I think. Once you've triggered some alarms that says your I/O is perhaps not the best behaving, we'll do some things to limit you. So to a certain number of IOPS per second. But when we sort of look across the users, and when one is killing the file system, they get to go on Flash. And everybody else stays on the disk file systems and doesn't have to deal with these high-end users. And it's actually worked pretty well. We know we have at least one acceptance test that without the Flash layer we would never have passed on the system. And we've had a number of instances of users, despite all the infrastructure and hardware that we have, pegging the metadata. There was a good exchange just Thursday of last week that I was watching. Frontera has a fairly small user community, so we do direct support on Slack. And a user was writing in, hey, Scratch 1 is going slow, what's going on? And the lead sysadmin, Tommy, who most of you know, wrote back and said, yeah, that's your job. That is causing Scratch 1 to go slow. And it was a user who had been running on 1,000 nodes, cranked it up to 2,000 nodes. That's 112,000 cores. It was an NPI task per node. Opening 112,000 little files in a tight loop for a write. Worked at 50,000, killed them at 100,000, and it's like, Scratch 1 will be fine as soon as we kill your job. And you can see all this in Slack happening in real time, and Scratch 1 immediately recovered. But all the other users can keep going in that situation, so we've been super happy about how that works out. So the question then becomes, does the machine really work, and what are we running on it? And so we built Frontera, again, very different mission than Stampede, although architecturally it's a very similar system, one generation newer. But again, the idea here is to have a few dozen projects instead of a few thousand projects on it and really ramp up the amount of time we give to each user. So I just wanted to give you about a half a dozen examples really quickly of where we're running truly at scale. And so Alexei has run on effectively the whole machine, 7,800 nodes. He got really good scaling out to about 250,000 cores, 4,000 nodes, and then he essentially ran out of data, right? He has a 150 million atom system. And once you got past about 250,000 cores, there wasn't enough atoms per node or per core to keep that thing scaling. And the exciting thing for him is, holy cow, my 150 million atom system isn't big enough. I'm going to do a bigger one. And he's doing sort of pores at the nucleus of a cell. I could talk about the science for more than my remaining time. But suffice to say, small stuff. You have to work at the molecular level to understand it. You need a lot of atoms to get the bulk properties of the material, to do biomedical applications, et cetera, around this. But he ran for over a day on 7,800 nodes. And again, you can see perfect scaling out to about 250,000 cores for day to 2 day runs on all of these. So the stability was the thing that made me very happy. Greg, similar, he's at Chicago. So looking at some HIV-1 capsid proteins. Again, actually same code, NAMD in this particular case, for molecular dynamics. Got up to 500 nanoseconds. Again, did the biggest system that his team has ever run, one of the biggest biomolecular simulations in history. Again, over 250,000 cores sustained for about 2 days for what he ran. Carlton at Utah does lattice gauge. So this is quantum chromodynamics. So now we're in, that was molecules, and now we're down to subatomic for this kind of physics that he's doing. 16 times larger system than they'd ever been able to run on any previous machine. Got to 3,500 nodes, has suddenly realized that his code will actually scale to exascale without rewriting. He just needed a bigger machine, which he was very excited about, because they have an exascale problem that they need to get to. And he thought he was going to have to start over, and he's like, holy cow, I'm getting sort of order of magnitude bigger all of a sudden with the bigger machine and actually stable. And then Dan Bodoni at Illinois, another longtime user, is doing the type of stuff Larry just showed, but working in the hypersonic range. So this is for a Mach 6 design, perhaps not quite ready for commercial aircraft. The initial problem at the scale, again, of needing several thousand nodes for several days, they could replicate the structure to do direct numerical simulation of the CFD work of a structure in a 20-inch wind tunnel, which is the biggest Mach 6 wind tunnel out there at NASA Langley, because you got to move the air pretty fast for that. It's also sufficient to cool these chips around Mach 6, so nobody's still listening. So anyway, 2 MPI ranks per node, 26 open MPI threads per rank. He actually got super linear speed up to about 100,000 cores because he managed to fit the whole thing into cache. So the future of HBM here. If you fit the whole thing into your high bandwidth memory, it goes better. But again, linear speed up to half the machine, several 100,000. And then last, Paul Woodward at University of Minnesota. This is a really exciting one. So this is a stellar fusion kind of thing. He's doing the convective boundary mixing inside of a star, sort of different layers. It's 3D simulations alternated with 1D simulations, because even at the scale that he has, it's hard to do a full 3D on this. Again, something we need a bigger machine for. But again, probably one of the biggest computations that's ever been run in history. More than 7,300 nodes, just some 73 something that happened to fit the dimensions of his problem. So 400,000-ish cores, 80 hours without a stop and a checkpoint. So run 7,300 hours and don't reboot for 80 hours, right? So that is roughly, that's the equivalent of running a single system for 75 years without rebooting in terms of reliability. And this is the kind of reliability numbers you get out of HPC that you don't really get out of the cloud. And his sustained performance was over 588 gigaflops per node for that time. So this was more than 4 petaflops for 3.5 days of running this single computation. So clearly one of the biggest runs in history. So you may then ask, do you run any codes that are not these 30-year-old giant Fortran codes from the mist of time? And in fact, if you look at Stampede, HPC software changes really slowly, but we have a number of National Academy and former Gordon Bell winners like Mike Gurnis who have moved their workflows fully to containers on our HPC resources now. These are all Stampede problems, but the point is the containerized Kubernetes scheduled type stuff is getting into our mix. Dan Kaminsky at San Diego, Tom Hughes, who sort of invented finite elements, but getting Phoenix, which is a nice piece of software that only has like 600 dependencies, packaged in a container that can run on the system. Sharon's stuff at Michigan, colloidal crystallization, also running in containers. So the workload is evolving. So I have 16 seconds left. So thoughts on file systems going forward? I will tell you that there's a lot of cloud native and a lot of AI and a lot of object store out there. But for the kinds of users I'm talking about here, I don't see POSIX going away anytime soon. We need to find a way to keep POSIX moving forward. I think a lot of our users couldn't really adjust to the cloud model. I think a DDN employee once said, and I have, he may be a former DDN employee for saying this, but I've picked this up, that object stores are for applications and files are for people. And I sort of firmly believe that, but we have had some success starting to fracture the namespace just into a few file systems. The thing we've never done is really ask our users to tell us what part of this giant global namespace that we give you do you actually need to access. And I do think we could do a better job, and we're probably going to start socializing in job scripts. Tell us a little more about the data that you use in the hope that we might be able to do something a little more dynamic around scaling POSIX. So we will be talking about the next system on Thursday at the BOF. Come tell me what you want. BOF Thursday, 12:15, quick ad. And thanks to all the people who give us money and do all the work, of which I am not one. So it's those folks. So, and thank you. I'm only 20 seconds over. So.
Questions for Dan in the audience?
That's good. We're back here. Yeah.
Yeah.
Yeah. Uh-huh.
How to prevent user from messing up? I mean, do you follow them before doing this big run?
Yeah, so let's just say first-time users don't get that kind of scale of access. So, and in fact, to get on Frontera, you have to have sort of worked up through the other NSF-supported systems, like Stampede and Bridges and Expanse, or the Exceed systems where we do let first-time users run. But mainly, you control it by the amount of allocation you give them, right? So all of them go through a peer-reviewed proposal process. And you start, it says, well, I've never done this before. And you say, OK, you can have 10,000 node hours. And then it's like, well, I've used my 10,000 well, and I can scale to this size. And it's like, you can have 100,000 node hours. But Paul burned 500,000 on that one run, right? So, about 600,000 on that single run. But he's been, 25 years of maxing out the machines and making sure they're doing the right thing. But yeah, it's all peer-reviewed proposals for the large-scale access. Mm-hmm.